functional analysis class. This session is not intended to be long. 20, maximum 25 minutes should be enough. I took time to partially write what we'll be talking about, so as to make it short, straight to the point, and then you'll be going to the video to try to assimilate, understand, digest the content of today's video. I promise that we'll be going through some simple examples, particularly the example that the two examples in the notes. The two examples in the notes, I explain what should be done, and I tried to write down, but it was so messy with already the writings in the notes and extra writings on top. So I say, okay, let me write it in a clean manner so that it will be easier for you to understand. So that's what I'm going to address now, those two examples, for you to see step by step why we need what. Okay, so let's go straight to the slide. I mean, to this slide. We have the definition of our linear operator. I wrote it here again so that you will not have to switch between windows. This is the definition of linear operator. And you see that in the definition of the bounded, the norm of a bounded linear operator, instead of putting k, I changed to alpha, so that you will not think that this is the same k, because this k, once you find it, it's not unique, right? And maybe the one that is here is not the infimum, right? But now its norm is actually the infimum, that is the smallest for which this is true. So that if you take a k that is less than this, or an alpha that is less than this, this is no longer true. So that's the norm. So in other words, writing this, you can still write, of course, in terms of the norm. That is, you remove this k, you replace it with the norm. It's still true because it's the infimum. So this is still true if you replace k with the norm of t. It's still correct. Okay, the proposition is there. This one, we'll do that in a separate video if necessary. Okay, so this is the example. I try to quickly reproduce this. And okay, so I'm going to do this part. Let me open a new window, a new slide. Great, so that I can easily move from this to the next. Okay, so I tried to write the definition of L1, which you assume to know already. This is the definition. F is measurable, and the norm, the integral of the absolute value of f is finite. That's the one norm. And now infinity norm on R, of course, on R means that's defined on the real line. Same thing, f measurable, but the essential supremum of f is finite almost everywhere. Almost everywhere. Essential supremum is like the supremum, right? It's like the supremum. To say that it is finite, it means that for almost everywhere, for almost every x, the supremum of x is bounded. That is, it might not be true for x in a set whose measure is 0. That's why it's almost everywhere there. And remember that when you are in the capital L spaces, the function that we are using actually is a class. And if it is, I don't know if I will be able to have time or the possibility to record another video on classes. Remember question space. Please read that and try to understand what is an equivalent relation. Because if you have a relation between function, and it defines what we call an equivalent class. Now, the equivalent class is a set, and in that set, you select a representative. So when we say that F elements of capital A are classes, it just means that this function we are talking about is actually a class. It means that it represents a set. It represents elements that are in relationship with one another. For instance, let me quickly write it on top here. I will erase it. Let's say, because if you recall, we define, we say that F is in relation, right, like this. And the relation here we use with respect to mu, for instance, right? With respect to mu, that's the measure that we are using. So let me write it this way. So relation via mu with this one, if and only if the integral of f d mu is equal to the integral of g d mu almost everywhere. So almost everywhere, this is a relationship. In other words, you find the integral of each one separately, they will be equal except for x yes, this is correct, eh? That is this integral, because if you recall, for the L, if you are LR, we integrate throughout R. Because when it's like this, it means that it's R like this. Obviously, we don't write it, right? Remember that when we say this, it is the same as the integral all over the space, right? And then when we write this, we can put x here, and then d mu x. Now, if you remove this x and x here, because remember that the function is at a point. Okay, so that's what it means when you write this. So, but we don't put r. Now, if I put this, I'm saying that these two are exactly equal when you integrate all for all x on r. But in our case, it's not necessarily over all r. It is the two will coincide on r, but except there might be point on which, if we remove those points for which this is no longer true, right? Because when we say almost everywhere, it means that this will be true, except for some point x. But the number of that point is negligible. That's what it means. The measure of x for which this integral is no longer true, or when I say for x, it's maybe, I want to put it in a proper way. Actually, this is what it means. In fact, when we write, it's not r, but it's r minus. This is r. So the two integral will coincide over r minus n like this. Where I say lambda. Okay, let's use lambda as the measure. lambda n is 0. Right. So that's what it means almost everywhere. Good to know. So this is our equivalent class. It's an equivalence relation. Now, if these two are in relation, the integrals are equal, right? Almost everywhere. Now, I don't need to use all these different f for which the integral are equal. Among them, I just select one. That is, if I take f1, f2, maybe up to fn, and they are all in relation, right? They're equivalent. Let's say like that. If f1 is equivalent to f2, f1 is equivalent to x3, that is each other, right? Pairwise equivalent. Now, instead of integrating each one of them, I will select one among them. So this one is a class, and that class, you can denote it by this, or f with a dot there, or a bar, generally bar, to indicate that this is a class of function that satisfies this. So actually, I can say that a function is an element of this because it's a class. Because a class is a set of functions. Let's say f1 such that f1 and f are in relation, right? Such that f1 is equivalent to f. And there are many such f1. There are many, I don't know how many, but there are as many functions as there are, right? They are all there. And now, when we say that f is in LP, let's say for R or whatsoever for now, in fact, this f is f bar. It's a class. So it represents a set of functions that are in relation. So that is why we move from this LP, where you don't distinguish, of course, where all these are mixed, they are all mixed. Those who are in relation, those are not in relation. Now we partition this, we group those are in relation. All of them, when we group them, we give them a name. That's a class. We give them a name, a class. And then from that, we construct LP, which is the coefficient with respect to this relation. I talked about that, but here I'm giving more details. Please read about it. The time is, I didn't plan really to go into this, but sometimes it's better to insist a bit for your understanding. Otherwise, I'll be talking about things that you will not grasp. It's not a waste of time. You are learning. Otherwise, you say you did math. If you meet somebody who knows this thing and talk to you about it, you say, I've never done it. They wonder how come you have a first degree in mathematics, you don't even know this elementary stuff. Okay, so it's up to you to buy proper documentation, read to upgrade. I mean, to have a considerable level corresponding to your degree, right? So that you are not surprised someday if you are discussing and you find yourself that there are things that you are supposed to know that you don't know. All right, so, okay, so let me. Okay, so I was talking about all these spaces. So that is it. You see, just to talk about these spaces, it took all that time. So, okay, so that is it. Let's quickly continue with this. Okay, F is linear. To show that F is linear is easy, né? First point. So let's quickly do this one. If it is first point. Linear because we want to show it's bounded, right? Remember that this is an example of linear bounded operator. So the first thing to show that it's linear is a linear functional. Functional just means that it is from functional. linear mapping. Generally, when you say linear mapping, it's between vectors. But when you say linear functional, actually, it's a linear operator. Linear operator. Okay. Because you have linear form or linear function as the same thing. Oh, anyway, that's not it. Okay, so it's linear. So that is it. So we are doing I first point. So I take F1, F2, two elements of L1 of R, and then I take alpha 1, alpha 2 in R, right? And also take X to be arbitrary and fix an arbitrary element, right? So I want to show that. Okay. So we want to show that F of alpha 1 F1 plus alpha 2 F2 is equal to alpha 1 F F1 plus alpha 2 F of F2. This is what we want to show. But in order to show this, I need to apply first this. I need to use the definition of the function capital F. And to use the definition, this is where it is defined. It is defined in terms of a certain X, right? So now I need to take an arbitrary X. Start from the left, I apply X to that, and then I expand and see if I get the right hand side. So for an arbitrary X, so I take it arbitrary. Because if it's true for an arbitrary X, it's true for any X. Therefore, we have the result. So I start from the left, right? So I apply X to that. So when I apply F, I can use the definition here. Of course, convolution, I don't need to write that. I go straight to the actual definition here. Okay, I wrote that this is equal to that. You can change, right? So that is X star G of X is the same as G star. So the order. You can change the order. So anyway, I can use any order. So this by definition. So this by definition is the integral. You see that when you integrate, it's all over R, right? Now we can see that we are integrating all over R because the function that we are using here are classes. So this the thing of almost everywhere whatsoever is waived when we take the quotient, right? No. Maybe I say something that's not correct. But anyway, so what I will do here, I will first write F and then G, right? That is this one first, and then the G will come after. So remember that if I have F here, I will say F of X minus Y and then G. So that F is everything here. That is this alpha 1 F plus alpha 2 f2. So this is our f. Now we apply it at x minus y. Now times g of y dy. Because you integrate with respect to y, it will depend on x. That's why you have x here. But you integrate with respect to y. So you have y here and y there. Because, okay, so that is it. So it is obvious that this one, I can take this argument throughout, because if I have f plus g of x, we all know that we can distribute like this, right? So that's exactly what we do here. That's why it's trivial, right? But I'm writing step by step, right? I just write it step by step there. So this will be, and we know that alpha f like this of x is equal to alpha into, that's time, f of x. So these are properties that are true. We know that the set of functions, right? The set of function, I don't know how to write the set of function. Set of function, I will not use from capital F like this. Set of function. I don't know how I will call it. Sure. I don't know how I will call that. Anyway, the set of function with these two operators, this is a vector space. So because it's a vector space, we have this. Anyway, so I will just apply it directly without justifying. You assume to be mature students, so that I will write it. I will just expand that directly instead of putting all these parentheses. I can use. So I'm writing this so that I will not justify why I'm writing. So I can write directly here. That is alpha 1 f1 x minus y like this. Right? Like this, plus alpha 2 f2, I close. Now I multiply by g y. Now I can expand again. I could have written that once, but if I multiply like that, so the alpha 1 f1 gy d plus the integral alpha 2 f2 x minus y dy dy. I can take the alpha out because the integral is linear. Integral also is linear. So I just take that alpha 1 like this, and then f1 x minus y gy dy plus alpha 2 integral f2 x minus y dy dy. Now, if you look at this one individually, you see that it's capital F of f1. Just look at the definition. So this is alpha 1, capital F of f1, plus alpha 2, capital F of f2. Yeah. Let's scroll up, and that's what we wanted to prove. So that's linearity is really trivial. And the next, sorry. Okay, the next thing now is to show that the convolution product of f and g is C infinity. In other words, its essential supremum is finite almost everywhere. Right. If we can show that first of all, this G, we say that G is C infinity here. You see, G is C infinity from here. Is it C infinity, and it's bounded. It's bounded. You can even see from the graph. You can see that it's bounded, right? From the graph, you can see it's bounded. So because it's C infinity, it's bounded. While it's bounded, it's essentially the essential supremum is finite. Because if I'm bounded, I can write that I'm less than or equal to fixed for any x, right? If that's the case, it means that it's also essentially the essential supremum is finite. So therefore, it is in L infinity. So that is what we have here. That's the information we have here. Okay, so I will use the fact that G is in L infinity to show that this capital F is bounded, because that's the, you want to show that it's bounded, right? Capital F is bounded. Right. So to show that, we will show at the same time. So by showing that this is L in L infinity, we will use one stone to kill two birds. So that's what we are going to do. Second thing. Ooh. Time. Okay. Two. So we know that I'm using this, I just justify G is in L infinity. All right, so it's there. Okay, so to show that something is here, just to show that it's bounded, essentially bounded. So I take X arbitrarily fix it there, right? And then I compute this. We know what it is. We know that is this integral. This is what we know. Now I take the absolute value of this, right? And is equal with the absolute value here also, right? But this is less than or equal to the integral over this over R of this. I can see right absolute value, but I don't need to put the absolute value on d of y, because you can see that g is always positive, right? Here you can see it's always positive. So there's no need to keep the absolute value there, but I can leave it dy. Right. Okay. Now from here, we know that this f is an element of L1. And this is an element of L infinity. That's what I wrote here. Okay, that's what you call Hilbert inequality. Hilbert inequality in LP spaces, and even in the tutorial. Is it in the tutorial? In one of the tutorials, right? I think that there are problems on Holder inequality. So if I use Holder inequality, because this is what Holder inequality states, if I have P and Q, that is P and its conjugate, of course, two natural number. So P and Q are conjugate of one another if we have this relation, 1 by P plus 1 by Q is equal to 1. Therefore, we say, so if you have this, we say that Q is the conjugate of P and vice versa. So this is called the inequality. Now, if I have, so P and Q are such that we have this. Now, if F is in LP and Q in F and G is in LQ, right? This implies that the product F G is in L1. So in other words, if I have P and Q satisfying this condition, F is in LP and G is in LQ, then this integral is finite. The integral of the product of the two is finite. That's exactly what Holder inequality means. So N we have. So we have these two results with Holder inequality. I'll write it directly, and we have absolute value is less than or equal to norm LP, or we can just put P there without the L for F, the first one, and then G, LQ. So this is all the inequality. And you can see that if this is finite, because if F is in LP, and it means that this is finite. And if G is in LQ, this also is finite. So the product of two finite is finite. So if this integral is finite, then whatever is there is in L1, right? So this product is in L1. That is, it is integrable, or the modulus is integrable. You see that here we did not raise this to any power and taken the. You can raise this is like 1 and then all 1 by 1. Whereas you know what this means? It means that you have the integral of the absolute value of, of the absolute value of F to the power of P, and then you take the pth root of that and the other one. So that's exactly what. So this is Holder inequality. Holder inequality. So that is it. I will leave it there. So that's what we use. So, okay, now let's look at our situation now. F is in L1 and G is in L infinity. If you go back, look at this. You can see that the F there are in L1 and G is in, that's what I wrote here, in L infinity, right? So I can just say F being in L1 and G in L infinity, that is, P is equal to 1. If P is equal to 1 and Q is equal to infinity, now let us see if this condition is satisfied. 1 by P plus 1 by Q is equal to 1 by 1 plus 1 by infinity. So this is 1 plus 0, which is 1. So you can see that's 1. So I'm done. So by all this inequality, I conclude that this product is finite, right? So by Hölder inequality, so that's exactly what I'm using. By Hölder inequality, I can now use a change of variable here just to call this a certain capital X, right? And this is certain capital, yeah, with the same X, right? Because you can see that it's the same X there, right? You can use a change of variable to show that. Yeah. So, okay, so from here, I just use Hölder inequality to conclude, right? I just use a Hölder inequality and I conclude. I conclude the result. Okay, I think the time it's really, the time is really advanced, but in the notes it is more developed, right? Because in the notes, the fact that this is essentially bounded, you can just take this, you can take the supremum of this outside. I mean, you can do that directly, or we can use this other inequality sort, or you can use directly the fact that this is essentially bounded, so it's actually bounded as we said already. So you can take, because this will be less than with the supremum, and then you take the supremum outside. Now, to the change of variable, this will be a single function. And you see how the result exactly as it is stated in the note. Please go there in the note with this explanation. Things will be clear. It's late already. Here it's already in 1913. So I will stop and I will continue later in another recording. Thank you for your kind attention. God bless you and see you next time. Bye-bye.